Hey guys, Mr. Barnes here, bringing you a little video, and this one's going to be on sort of an explanation of the Doppler effect. So the Doppler effect is the apparent change in frequency of a sound from an object, maybe a police car, fire truck, screaming baby, as it moves to an observer watching or listening to that sound. So let me give you an example. So if I have a screaming child here, let me draw a little baby, no different than my little baby who's in that screaming phase. So if I have a screaming child and he is wailing at the top of his lungs, he's emitting a sound. So I'm just going to draw, the sort of, we all kind of know the sound waves sort of look like this, right? So I'm just going to sort of draw that in sort of like if these were complete circles. So, and you can sort of picture it going around the baby's head as he's screaming his head off. These are circles of sound waves. It wouldn't matter where you're located, you'll still hear that. Like if that baby was yelling from here, it wouldn't be just someone standing over here that's going to hear it. Someone standing over here hears it as well. So you can sort of see that you've got these circles of waves, and these should be fairly evenly spaced apart. So this baby isn't moving at this point. So if someone was standing over here listening, and someone was standing over here listening, they would hear the same frequency. Now, if I get that baby, like my baby does to me, as soon as he starts crying, he runs away from me. So if I have that same baby, and he is moving in this direction, so he's still wailing his head off, and he give the little guy some ears, and he's still wailing his head off, but he's moving in this direction. So those sound waves, what happens is, as he moves, they sort of take on more of an oval shape, and I'll show you what I mean by that. So here's the first one, and the waves on this side become really close together. So the waves sort of bunch up on this side as he's moving in this direction, and they're sort of spread out over here. So you can imagine as these waves get closer and closer to this listener over here, he's going to hear a higher frequency as opposed to someone over here. So here he'll a high F, and this guy over here will hear a low frequency. So frequency meaning pitch. So he'll hear a high frequency, and this guy over here will hear a low frequency. So that's all the Doppler effect really is. So they're hearing the same sound, essentially, right? So the screaming baby, but based on location, they're observing a different frequency. So the actual frequency of the sound is not changing. The baby is staying the same, but based on location and the movement of that baby, it's causing the frequency to change. So what you should know is that as a sound or an object emitting a sound moves closer to something or move towards, so this is moving towards, you get a higher frequency. And this is a low frequency, so this one will be moving away. So mathematically what that looks like, and that was my best baby drawing. Mathematically what that looks like is this. So I like to use F2 is equal to the speed of sound times F1 divided by the speed of sound plus or minus the speed of the object. So this is what, this would be the baby scream. So the actual frequency. This would be the observed frequency. So that's what the listener hears. That's what the person standing next to the screaming baby hears. So this is the speed of the baby. So the speed of the object. So if the baby is running away at a certain speed, then that will be that particular speed. And this Vs here will be the speed of sound. And one formula that might be particularly useful, especially if you're in like a lower physics course be this guy, 332 plus or minus 0.6 t. So if you have, so if you have a temperature given, you might have to find the speed of sound using this guy. So let's just show how this formula works. So let's just say that I have a police car, and its emitted frequency, so emit it F, and that's equal to, let's say, 444 hertz, and it's moving away at a speed of, say, 33 meters per second. And let's say the temp is 30 degrees Celsius. So we got the emitted frequency, so that's the police car is actually emitting, so that's what the police officer inside the car would continuously hear. You got the speed of the car is 33 meters per second, and the temp outside is 30 degrees. So basically what we have is we have F1, the actual frequency, which is 444. And then we have, speed of the object, 33. So we also have the speed of sound. We just need to do a little bit of work to get it. So 332. That shouldn't be plus or minus. That should be just plus. 332 plus 0.6. So my apologies if anybody jumped through the computer then. So what's he doing? I know YouTube. They get angry with my mistakes. I'm just working out this number here now, guys. So that's, I put my 30 right there, and I end up with 350. I'm almost running out of space. Hopefully that stays in the screen. So that answers, let me shift it up a little bit. 350. So let's see. So now that I have those things, one of the things that I had to recognize is this keyword right here, moving away. So we got this plus or minus, guys, right here in the formula. So I don't know if you guys can see that. I'll wheel it down a second. So we got the plus or minus here in the formula. So it's important to recognize that we use the plus when the object is moving away. And I should have explained this before probably. And the minus when it's moving towards. So the reason why we do that, we just talked about, let me bring the baby up for 1 second. Just talked about how that when it's moving towards, it's a high frequency, but we're moving away, it's a low frequency. So in terms mathematically, what that means is moving towards, there's a high frequency. So we want to, these numbers on top aren't going to change. So we want to divide by a smaller number. So we subtract away the speed of that object. Whereas when it's moving away, it's a low frequency, so we want to add up those two numbers. So what it means for our problem that we're doing here is we have the plus. So speed of sound plus speed of the object on the bottom of that guy. So we end up with, so F2 is equal to, and then I'll fill this guy in, so the speed of sound is 350. And then I got my frequency, the actual frequency, which is 444. Divided by, and then I got my speed of sound, again 350, plus my speed of the object, which is given to me in meters per second, 33. So then I can just go ahead and do the math on that. So I'm not a guy that likes to write a lot of workings down, guys. I believe in getting straight to the point. So the top part, if you're working it at home, is 155,400. So let me just try that. 155,400 divided by 383. So I just add at the bottom. Oop, let me get my calculator right here. Actually, I'll put my calculator there. So let me see. 350 plus 33. So I always do that just in case I made a, even though I'm kind of confident in that, obviously. But if I made a bonehead mistake on a test or something like that, I generally try not to trust myself. Make sure I, don't be lazy about it and make a simple calculation mistake. So what I get is 405.7, so 406 hertz. And there it is. That is using the Doppler formula and a short little explanation of the Doppler effect, guys. So I hope this helps you, and I'll see you guys in class. Thanks for watching. And subscribe and like to my YouTube channel as I search for the off button for this camera. Thanks, guys.